Hi, welcome back to es346 Basic Thermodynamics. This is Module 3.4, the ideal gas equation. The section in the textbook is section 3.6. Here are the two learning outcomes for this module. At the end of this module, you will understand when a fluid behaves as an ideal gas, and you'll be able to use the ideal gas equation to calculate the gas's properties. So let's go back and look at the phase diagram that we had with the PDT relationship. And from the diagram, we know that a material always occurs somewhere on this surface. And if we wanted to know, for example, what the pressure was, we would need to know just the volume and temperature. Then we would come down to the table, find the corresponding volume and temperature point, and then we would read off the pressure. Now, reading off diagrams isn't really easy, so engineers tend to use tables. So the last couple modules we've been looking at using steam tables. And here, for example, again, given a pressure, like 0.5 megapascals, and given temperature, say 600 degrees, we could go ahead and read off what the corresponding volume is. Now, this works pretty well, but it also requires a lot of effort. And sometimes it would be nice if there was something a little bit easier. And it turns out that there is. There's the ideal gas equation, which you probably remember from chemistry and physics, is PV is equal to nRT. And this is also a PVT relationship. There's P, there's V, and there's T. So if this product of N and R is constant, we could go ahead and use this equation to find properties. Given P and V, we could find T, etc. So it functions the same way as a table or as a diagram. Now, one of the things about the ideal gas equation is it does not always give me a good representation of real behavior. Let me write it up here again to remind you. PV is equal to nRT. And what this diagram shows here, this is a plot of temperature as a function of specific volume. And remember, specific volume is simply the volume over the mass. And this is what the error is in the ideal gas equation. So here where we've got the volume, this would be the volume coming from the ideal gas. Then there would be a real volume. Call it V real. And so here what this shows is the error, the difference between what the ideal gas equation predicts and the actual volume. And what you'll see is over in this region that's shaded, we see the percent error, and it's 0.0, 0.1. It's very, very small. That means the ideal gas equation is a good representation of the actual behavior. Now, as I get further over to the left side of the diagram, I see larger errors, 2.6, 17.6, 37. Those are really large errors. That means the ideal gas equation does not do a very good job of representing the actual behavior. So one of the things you need to be good at doing is determining when can you use the ideal gas equation. Well, let's go back and look at this diagram. And these green lines, if you remember, those are isobars, which are lines of constant pressure. And these isobars that are over in the hatched region are like 100 kPa, 10 kPa, 0.8 kPa. So those are all low pressures. So if you have a low pressure gas, you can use the ideal gas equation. Now, as you get to higher and higher temperatures, you start to be able to go to slightly larger pressures. So for example, over here at 600 degrees Celsius, I can then be using a pressure as high as 1 megapascal with only 0.5% error. All right, let me say something about the gas constant R. So here we have the ideal gas equation as you're probably have you seen it before in perhaps chemistry and physics, where N is the number of moles. Now, that's not a very convenient form for engineers. We don't like working with moles, we like working with mass. And the reason behind that is the number of moles can change when a chemical reaction happens, like when you burn a gas. And therefore it's not constant, whereas mass remains constant in a system. So what we often do is we multiply this by 1, but we multiply it by the molecular weight over the molecular weight. So that's 1. So that doesn't change this equation. However, if I look at N times the molecular weight, that would equal the mass. So I would have this form of the equation, PV is equal to m. And now what I have is Ru over the molecular weight. I'm going to call that simply R. So that's the R that appears in this equation. So PV equals mRT is also the ideal gas equation. Here we have a mass that will have units of kilograms or pounds. And the value of R, which is the universal gas constant, divided by the molecular weight. And that's why I put a sub U on it when it's the universal. So for example, that has the value of 8.314 in SI units. And in English, it's 10.73. Now, one of the consequences of using this value of R is that it's different for every gas, because each time you're dividing by its molecular weight. But you can find these values of R. They're in table A1 for each one of the gases. Now, there's one more thing we often do, is divide both sides by the mass, whereas this right here becomes the specific volume. So you have this form, PV equals RT. And this is nice because this is, again, we see these three intensive variables, PV and T. And so given any of those two, we can get the third. All right, let's go ahead and do an example using the ideal gas law. And this question says I have a tank of nitrogen. It's 2 cubic feet, 5 pounds, 70 degrees Fahrenheit. And I want to know what is the pressure. So I'm going to use the ideal gas law. PV is equal to mRT. And one of the things I need to do now is look up my value of R. I looked it up on table A1. And I see that is 0.383. And the units for this are PSI, cubic feet, pound mass, R. And that comes from table A1. And that's actually A1E because we're working in English units here. So now when I use this value of R, I'm going to want all of my units in, for example, PSIA in cubic feet. So let's go ahead and do that. We've got P is equal to mRT over the volume. And let's plug those numbers in. We have 5 pound mass, 0.383, which is my value of R. Temperature, which is 70. Now notice this is degrees Rankine, so I need to convert my Fahrenheit to Rankine. I need to add 460 to that. And now I'm going to divide by my volume, which was 2 cubic feet. And if I do that arithmetic, plug it into my calculator, this comes out to be 507, and my units are PSIA. All right, let's continue with this example. And now the problem says some N2 escapes until the pressure in the tank is dropped to 200 PSIA, and we want to find out how much N2 has escaped. So again, I can use the ideal gas law, but I'm going to rearrange it to solve for the mass. So mass is PV over RT. And we'll find out how much mass remains in the tank. And so if my pressure is 200, the tank has a constant volume, so that remains constant at 2. My value of R, 0.383. And then my temperature, which was 530 Rankine. That's 70 plus 460. And this comes out to be 1.97. The units are pound mass. So how much mass left? Well, that would be 5 minus 1.97, or 3.03 pound mass.